I got some mumbling. I didn't try to overheard anybody, but take what I'm saying with limited seriousness, and I might change my mind a bit, but I'm not crazy about a system where you have 2, 3, 5 exams in 1 day, in 2 days. I think that exams should be taken seriously, and it should take some time before that to seriously prepare for it. So if you are in a case where you have a cluster of exams at the same day as ours, or just the previous day, and you have really good reasons, don't take advantage. Let's talk about it. If you're such a scenario, and maybe I can tell you, come back. I cannot wait with the grades too much, but I can squeeze maybe a couple of days if that is really what would save you. Then, and you have a good reasons, but talk to me earlier. Okay. We are continuing with dynamic programming. Hopefully today you have finally the midterm results. And I taught LCS numerous times, really unbelievable amount of times, and I always I didn't like the way that the book described it. I changed the slides today. Hopefully it will end up better. The LCS algorithm, even if you have seen it before, at least I present it differently, even though the algorithm, and you will see it in actually all the examples of the dynamic programming algorithms. I will speak and speak and speak to death about it before we really get to the code. And once you'll see the code, then it will be just a very few lines of code. The explanation before are always much, much longer than the algorithm. It's one of the common thing about all dynamic programming algorithm. And another common thing will be that there is lots of indices, and matrices and tables, and sub-indices, etc. Okay, before that, questions about anything? Oh, good. Okay. LCS, to remind you what, quickly reminder what is a question. You have 2 strings that I write over here with letters inside, and I want to find a matching of character to characters. The characters needs to be 1-to-1. I can only match xi to a single yj and vice versa. I can match them only if they contain the same letter. Say B and B are potentially a good match, but not necessarily. Maybe this B will better go with this other B, but I cannot match B with A. And I'm trying to place as many segments as I could, and I don't allow crossing segments. That's essentially the LCS problem. Now, there is a little difference between the LCS itself versus the alignment. Term alignment will usually say, if I match this, in this example, if I match A, B, B, A with A, X, which is A, B, B, A, with Y, which is A, B, A, then the length of the LCS, not too hard, it's 3. I can match at more 3 characters. And so the LCS of X, Y is, of course, A, B, A. But alignment-wise, or matching-wise, there are 2 matchings here. But I have one. I have the blue matching, which would be one possible matching. And I have the black matching, which will be another matching. So this is usually referred to as alignments versus just the length of the LCS. And our problem would be, of course, given these 2 strings, find the LCS. Now, LCS in the longest common subsequence. Subsequence, as opposed to substring, it's a solid term in mathematics. I think that in all the contexts that I saw it, it always means the same. You can delete any characters that you want, but you cannot switch orders. And characters in particular don't have to be consecutive. Okay. And LCS, we'll see, have a close relative, which is the edit distance. And edit distance has a relative called Viterbi algorithm that talks about hidden Markov models. And they are all very much matched together about as possible explanations. And we'll see more about it when we'll get to the edit distance today. Okay. If I ask you in the homework, if I gave you a subsequence of x, find if it's also a subsequence of y, but the subsequence of x is given to you. It takes only linear time. Just use naive greedy algorithm. And but if I check all the possible substrings, it will be exponentially many. All the subsequences, actually. It would be exponentially many, which implies that I need to use a, I don't have the chat, that I need to use a, that I prefer actually to use the length of the LCS instead of the LCS itself. Notation. You look at a string, ask how many characters you have in this string. And string and sequence will be the same for us. I use these terms interchangeably. So when I put a string and put 2 bars on the side, how many characters I have in the string? Cij that takes lots of wording and it's convoluted sentence. What is x from 1 dot I? It's a prefix of the first I characters of x. X equal hello, then x of 1 dot 4 would be HELL. That's x from 1 to I. Y from 1 to j, just the same thing. The prefix of the first j characters of y. Find the length of their LCS. Now, the length is unique, of course. What is the LCS is not necessarily unique. You can have different subsequences that all give you the same length. Put the length of the LCS. Put the bars on the side, make it the length of this LCS, unique term, well defined. This is what Cij is going to be. Okay, now, what do we need to return at the end of the algorithm? And I mentioned it in the end of last class. We will first solve the problem of find the length of the LCS. And then we will reconstruct what is actually the characters in the LCS. The same way, using Dijkstra, finding the distance from here, finding how to go from here to Phoenix will work as Dijkstra works in 2 steps. First, find the length of the path, of the shortest path from here to Phoenix. And after you know what is the length, and from various information that the algorithm leaves for you, well, breadcrumbs that the algorithm leaves for you, you can reconstruct the path. So we first want to know what is the length of this LCS. Okay. And here I start to move into my explanations that are, well, it will get to the same conclusion like the CLRS textbook and many other textbooks about algorithm. It's a very classical topic, but I'll present it a bit differently. So I want you to think about the last characters of x and the last character of y. Sometimes I'll refer to both of them as character n when I'll talk about complexity. Here, let's be a bit more careful. I assume that x have m characters, so I'm looking at the last characters of x, and I'm looking at the y character of y over there. you can kind of know from which years an algorithm comes based on how they start to counting at 1 or 0. So we start counting at 1, ending at n. And I want you to look at the last character of x and the last character of y. And now I split it into 3 cases. There is some optimal matching. There are different, we said LCS is not necessarily unique. Let's imagine that somebody gave us the optimal matching. As many segments as you can, as many characters as you can. So you look at this optimal matching. And in this optimal matching, possibly a character is left unmatched. Character of x or character of y is left unmatched. Or if it is matched, it's matched to exactly 1 character of the opposite string. And our rule was no segments crossing, and it's 1-to-1. And of course, a character can be matched only to a cell that contains the same character. So look at the last character. Let's assume our first case is that the last character of x is matched, that the last character of x is matched to somebody, maybe this guy, this b over here, and in addition, the xm and yn, the last 2 characters, are the same. Claim nothing better will happen if I'll take these segments in the matching and move the segments to match to the last character of y as well. I mean, what can go wrong? Maybe I'll get less of a price, but we said that our price model is that every segment gives you $1, give you the same price. Even if I had price, as long as the price is not depending on the location, I'm good. If I have like a different price per every character that I matched. There is a very good reason to ask about the weighted issue, but we can put it aside. So I'm trying to find maximum number of segments. Take this last segment. If it is not matched to the last character of y, just move it. So what can go wrong? You don't change the price. Is there any chance that you cut any other red segment in the optimal matching? No, because any other red segment that is would try to match somebody maybe here to somebody here, which cannot be because it will cross your original match. That is, this type of a shift will not cause this last segment to cross anybody. It doesn't mean that at some point in the future it might not be an issue, but at the moment, this segment doesn't cross anybody. What will be the price stays the price. So I can assume that in case 1, that is LCS of that I'll match the last 2 characters. Again, under the case that xm and yn has the same letter at the end. OK, that gives me an insight about how can I express the length of the LCS of the whole string of m and n. Right? Because once you all agreed with me, hopefully, that I can match the last 2 characters and not conflict any other matching, it means that I can now take a big eraser and delete the last b and delete the last b from here. Yeah, let's demonstrate it. On the board, I have A, B, Q, R, F, N, L, L, F. No, L, L, A, L, L, F. 1, 2, 3, 4, 4, 5. The last 2 characters are the same. Let's match them. And now, possibly there are other segments in my optimal matching, which of course I don't know. It's chicken and an egg. That's what I'm trying to find. However, once I decided that I can match them, I can greedily delete all of them. And now find a solution to a somehow smaller problem. What is my smaller problem? Find the LCS, in this case, but of x whom? X, which is just from 1 to 4. Not from 1 to 5, because f is taken. And y, which is 1, 2, 3. F is out of the game. Okay. Or in general, the length of the LCS in this case would be the length of the LCS of drop the last character, delete, erase, remove the last character. You have two smaller strings of length m-1 and n-1. However, your cost of the LCS now gain one segment that is in the bank, is secured. Okay, so in this case, putting it in our shorthand, somehow confusing notation, let's have this notation written on the board all the time. C of ij is the length of the LCS of x1 dot I, y from 1 dot j. There's a cost. OK, that was the easy case. Now we need to handle the case that xm is matched, but xm and yn don't contain the same character. And similar the case that xm is possibly not matched at all. So here is an example. The last characters of x has b in it. The last characters of y has c in it. Yeah.
Just to clarify, C is like a matrix, like you're updating when you calculate or find those.
If I'll follow the book, I'll say C is just a variable that I'm playing with, some abstract thing. The way I'll present it is, yes, C is an array. Okay. And so I'm diverging from the book's order. But yeah, C is going to be just a matrix. OK. What's the length of the LCS of these two beautiful strings? Looking for a set of segments that don't cross each other, there is only two of them. If you try to add the C, if you try to match the B to the B, it will, the disqualified sign, if you know. Okay, so we have crossing segments. Okay, so it's also an example where xm and yn, the last two characters, are not the same one. So does it mean that I cannot match them? Well, yes and no. They definitely cannot be matched to each other. I cannot match xm to yn because they don't hold the same character. It's B versus C, where in the case that xm, yn are not the same character. So the option of them match them to each other doesn't exist. What else can be? Possibly I'll match the B to somebody that happens before the last character, and I'll try to match the last characters of y to somebody that happens before, but it's obviously that cannot happen. But if I'll try to match the last character to, it's not the last character of y, somebody that happens before, that's this blue segment, and at the same time I'll match the last characters of x to somebody that happens before, that's a red segment. No matter what you'll do, try and prove by example, these two segments will cross each other. Conclusions, I don't know if xm can be matched or yn can be matched, but it is impossible that they are both matched. At most one of them, possibly zero, but at most one of them is matched. I cannot match both the last characters of x and the last characters of y without getting a conflict between them. So what? So it means that in the maximum length of the LCS, in the optimal matching, the last character, say you claim that the blue matching is the optimum, then if I'll delete the last segment of the last entry of X, it will not affect the optimum LCS. It's redundant sentence. LCS by definition is the longest, but it doesn't hurt the optimality if I'll just try to match a shorter segment. My problem is express a big problem in terms of smaller problems. If I'll delete this last segment, it will not hurt if you're claiming that this last segment, this last character don't participate in opt. So delete it. It will not hurt the optimum length of the LCS. Right? So I can consider match all of X, so match, oops, I got a typo. Match, yeah, so the typo would be, LCS in this case, LCS of xy, would be we said I don't need the last characters of X. LCS of X from 1 dot m minus 1. I deleted the last characters of X and match it to all the characters of Y. So I'll just shorten it in the length of Y, all of it. But wait, who told me that it's the last characters of X that I should delete? Give me a sec. Possibly it's the last characters of Y that I should delete, which I did write properly as the length of all of X to all the characters of Y minus the last one that you deleted. Yes?
If you said this, I just want to make sure that I'm understanding it correctly, because I think it says it differently on the slide. It says that at most one of X, M, or Y are unmatched and off, and this isn't the case where they don't match. They can both.
Not when they are the last characters. Not when they are both the last characters of X and Y.
So
I think that I know where you're going, but note, again, the case of that they are the last characters respectively of X and Y.
and you're saying they can, there is no case where both of them will not be.
Oh, I see that it's double negation.
Yeah.
Conclusion,
One right above the conclusion.
that is at most, yeah, thank you. Okay, there are two typos, so let's spend a moment. Yeah, I'm sure that you all heard it, that in the logic lesson, the teacher is saying that it's interesting that double negation is not, double negation is not positive, but double negate. Okay, you know where we're going. Never mind. I killed it. It's too early in the morning for me to get to. So that would be the LCS of all of X 1 dot m minus 1 to all of Y. And we said that is unmatched. Slides from yesterday. Okay, so I don't know which one I should delete without hurting. I don't know what. You see two matchings, they are both matched, but not at the same time, and I need to delete the one that doesn't hurt the matching. I don't know which one, so, but the point that I am sure is that one of them could be deleted without hurting the optimality. So here I'm looking at the maximum length when the last character of X is deleted, and possibly this is the length of the LCS of all of X, all of Y. Here is the length of them when the last characters of y is deleted, and x stays the same. And that would be the length of the LCS of x and y. Anyhow. Okay, so in this example, of course, it's a b that I can delete. So I'm looking for the LCS of c b with the whole of y. And again, I can delete the other b as well without hurting the optimality. And now you're left with a problem of matching. After these two deletions, because it's recursive, you want to ask what is a LCS of CC and a DBCC. Okay, if everybody believes me so far, now we can sum up all these cases. By the way, notice that in the previous formula, I did not say that, I said one of these two is not matched. I don't say that the other endpoint is necessarily matched. That's definitely not what we are saying. It's possible that both these characters are not matched in opt. Important notation. One of them is definitely unmatched, and possibly both. Okay, summing up these two cases and using our new notation Cij, then if xi and yj are the same, then Cij is just 1 plus ci minus 1, j minus 1. And if they are not the same, and notice that here and if they are not the same, xi and yj are not the same, then Cij is a maximum of ci minus 1, Cij minus 1, I minus 1, and j. But now wait. You have the definition of what is Cij over there, but all this time, when I pulled this theorem, I was talking about the case that it's the last characters that is important, the last characters of x and I. Suddenly I'm using I and j that might be in the middle of the string. I think that is an excellent point to be confused about. Who allowed me to talk about I and j that are the middle of the string? And the answer is that, look at this definition. Here, the definition of Cij assumes that you are just matching the prefix of the first I characters of x. That is, when you are thinking about the Cij case, you are completely oblivious to the fact that there are more characters after x, after the I characters of x. You want to compute this value, you just cared about the first I characters of x, and in this case, I is the last characters of this guy. Similarly for the y. There are no more characters, you just match the prefixes. Okay, so if everybody is happy with this theorem, then let's see a sentence that will say, even it might not be fully clear. A place where you can use dynamic programming is when you see that the optimum solution to the problem contains optimal solution to some subproblems. It takes a bit effort to see it in the LCS. So I want to say, if you, not every two prefixes makes a good match between them, but there are I and j that are the good prefixes. Let me explain it in two cases what this optimal substructure tries to say. First, the cut and paste lemma from Dijkstra. So Dijkstra, the cut and paste lemma from Dijkstra, but we are using it in all the dynamic programming problem, says, and I highlighted it last meeting, that I want to find the shortest path from F to T. Shortest path. I know that there is some shortest path. What is the structure of this shortest path? Assume that Vi is a vertex along the way. I don't know if Vi is actually, when I look at the graph, I don't know if Vi is along the path. But if Vi is along the path, then what is the shortest path to Vi? Take the optimal path and just delete from it everything that is relevant to reach for Vi. Why do I call it a cut and paste lemma? Not my terminology. Why the book? Cut and paste lemma because if you had a better path to go from S to Vi only, that costs 16 while this costs 17, then you'll also have a better path to reach to T. But length of a path is what the sum of weights, or the number of edges along the whole path. If you had a better way to get to Vi, then you'll use it as a better way to reach to T. It's this plus this is cheaper than this plus this. So the original path is not the same. This instance in the case of the LCS would mean that if you just pick I and J, some oracle told you exactly what is the LCS of the I and J, what are the optimum value of I and J, then you will use the substrings, the subsequences, to build longer and longer subsequence. Let me try to show it geometrically. Here is X and Y, and here is my optimum matching. There is an optimum matching. If this is optimum matching, it means that there is some I and J that the LCS of X, Y, the whole thing, has the same length as the LCS of X of 1 to I and Y from 1 to J. Right? If this is the optimal, what I drew in red. So in particular, look at the last characters of the I and J and delete everything else. Nothing hurts if I delete everything else and just find the LCS of these two prefixes. And the previous theorem tells that it's just 1 plus the LCS of delete everything right here and delete them. And you now have even shorter prefixes that you find their optimum solution. If you had a better solution for the I minus 1 J minus 1 case, then you can use it to make it a better solution for the whole problem. Make sense? So but it doesn't mean that I can pick I and J arbitrarily. It's the same, I'm making a big deal out of it because we'll see the same principle in 5, 6 examples. It doesn't mean that I can pick I and J arbitrarily, and that's why this algorithm is not linear, because there is a lot of pairs of I and J that I need to check. Oh, sorry, I thought that I deleted it. Maybe we'll go back to it. OK, so what is the algorithm? Maybe it's not the latest version. So LCS of X and Y. For I what is C of I, comma 0, no matter what is I? I'm trying to match a string of I characters to a string of 0 characters. How many segments can I put? Exactly 0. So C of I, comma 0 is 0. A good way to lose points in the final and homework is don't do the initialization. A lot of the algorithm. Yeah. The same goes for J from 0 to N. C of 0, comma J, 0 as well. And now for I goes from 1 to m, for j goes from 1 to n. If xi and yj are the same, should be 0, 0, should be equal, equal. Cij is ci minus 1, j minus 1 plus 1. No matter if you pick the correct ij or not, it still holds. And if xi and yj are not the same, then cij is just a maximum of ci minus 1j, cij minus 1, what we saw before. And that's all algorithm. That's it. Dynamic programming all have a very, very short code. But there is some critical element here that's worth explaining. Let's think about computing Cij. Here I assume, oh, let me write the same code in a different way. Not the same code. Let me make an attempt to write this algorithm again. And if you see the bug in my writing, please let the other people figure it out. Init, same. I'm not copying it. And okay. Meditate on it, and then I'll pick random student, arbitrary student, to tell me if it will run the same way or not. The init is the same. And now I start from I equal m, or for I equal m, as long as I is larger or equal than 1, I plus I minus minus, if you are never seen the down to. It's old code. Okay? And the same for j. And it looks quite similar. Running time is the same. You're running through all the cell of the table and so on. It's a big deal in terms of the dynamic programming. It's when we, and I'm teaching you dynamic programming as a really useful tool for many, many, many other problems. It's not that it's just LCS. So in this particular code, it's very easy to find a bug. From the people that are usually here less, no, sure.
The C I minus 1 and j minus 1 have not been updated yet, so they have like zeros, or they don't have the correct values.
I have no clue when I'm computing this length what is this number in this case. That is, the fact that it's almost accidental that this algorithm works is because we only make our strings longer and longer, but every sub-problem that we are looking at, we'll see it less intuitive in other cases, every sub-problem that we need the answer to, what is the length of the LCS, is already computed. Okay. And by the way, a stupid homework question might ask if I want to update the LCS itself, not the length of the LCS, then what should I do in each one of these cases? I have to push around substrings all the way. So each operation now takes at least linear time, just as in Dijkstra, if I would ask a vertex to update another vertex by the whole path, there is a lot of information that I need to update. Very not efficient. Okay, so that's the algorithm for the LCS. Running time, not much to argue if M and N are arbitrarily. I asked you in the homework question to ask what the case if they are almost identical. Identical up to k characters. If they are identical in the homework, the general case that I asked you about was if the length of x equals to the length of y, and they are identical up to identical up to k characters. And k is somehow small. What's our motivation here is that we have big files. You worked on it overnight. I worked on it overnight. We want to ask what is the difference between our versions, but the differences between our versions are much smaller than what is common. So in this case, you can reduce the running time to n times k. Okay. It's not hard, but it's less obvious than the other questions. Space, here is a big discrepancy about the space. That I said that it's not an issue that I do or I don't update the strings, but if we'll see that if I want to reduce the space, then, and I just want to know what is the length of the LCS, I can do it with linear memory. I will not go through the whole algorithm, but essentially that's the array C that we are getting. And essentially looking at this T, at the C over here that contains 2 after the algorithm runs. Why does it contains 2? I cannot match A to C. These are C4 3 X4 and C3. I just picked a cell at random. This guy is well, A does not match C, so Cij, which rule are we using, equals to the max of Cij minus 1, which is 1, Ci minus 1j, which is 2. That's why I wrote 2 over here. Okay, it doesn't tell me that it participates in the matching, in any optimal matching. It just tells me that what is the value over here, the maximum of the cell to the left and the cell above me. Why did I write 3 over here? Because I can match the A to the A. So Cij equals Ci minus 1, j minus 1, go diagonally, and add 1 to it. Or if I'll ask you about the weighted case, where every character has a different weight, add the weight of this character. It doesn't mean that this is part of the optimum solution. It definitely doesn't mean that it's part of the optimum solution. I will not know what is the optimum solution until I filled up the whole table. And I'm looking at this cell at the top right, at the bottom right, and ask what is the value of here. And now I can pave my way. You're glad I let you figure out yourself how, but I can pave my way along one of these paths. There is a lot of paths that starts here and ends here. Oh, in Dijkstra terms, that will be the source and that will be the target. And here you have some graph. We'll use this analogy a few times. Think about it as a graph where every node contains a number, and it's a DAG, actually. You have arrows that only go down or diagonally or to the right. And in this DAG, I'll ask you to find a path that gives me the correct value. OK, so the big deal about it, for every cell ij, its value is uniquely determined by either the values to my left and the value above me, or diagonally the value that I have, depending on which of the cases of the theorem we have. And basically, to reconstruct the LCS, I'll go to the bottom right character, and I know now what is the length of the LCS, but not what is the LCS itself. And I can ask under which cases, go to the left or go to up. I can also, it will be more useful in other dynamic programming algorithms, I can also leave cram breadcrumbs along the way that will tell me how did I get this value over here, the 4. Even though it's not hard to know, there are only 3 candidate cells. And I can actually say, when I'll fill the 4 over here, I'll explain which of the other cells gave it this value. Just in the same way that when we are writing shortest path Dijkstra, every vertex that thinks that it knows what is the shortest path to it says who is the preceding of me, who came before me along the shortest path to me. OK. How can I reduce this memory? Well, memory is usually what kills the performances of your program, much more than the running time directly. The moment that you cannot put the whole array in your main memory, in the top level of the cache, you are going to slower memories, and that's what destroys the running time. So how can you make the running time a bit better? You can essentially, if you just want to know the length, then you cannot do it with linear memory, with exactly n or m memories. Let's say that they are both n by n. Otherwise, I'll keep confusing between the n and m. Let's say that they are both n times n, both of the lengths, same length. With only one array of n cells, I don't think that you can do it. But if you have 2 cells, then what's going on? You are taking the top row and use it to fill the second row. And once you're done filling the second row, then you don't need the memory from here. So you are using it, except that now you're calling it the third row. OK? You always alternate from one cell from one array to the other. So with 2 arrays, you can do it. And you can actually find the LCS itself by somehow log n such iteration, giving you an overall running time of n squared log n. So I'm not providing details right now, but we can LCS of xy could be solved with order n memory, but in time of order n squared. N squared is what the normal LCS takes times log n. And it requires a bit more tricks. That is. But this actually gives you what is the LCS itself. As I said, if you want to know what is the length of the LCS, then you can do it with linear memory with no tricks. Just use this choreography of 2 arrays. OK. And that's how I reconstruct it. You can leave somehow flags that will tell you how did you get these values, and then the reconstruction is even a bit easier. Not useful for the case of the LCS, useful for other dynamic programming algorithms that we'll study. OK. What can go wrong if I'm trying to solve the problem recursively? These are a few slides that I skipped. The book showed it in the reverse order. The books will start by what can go wrong if I try to solve the problem recursively. Is this a correct code? LCS of xy, look at the prefix of the first I characters of x, first j characters of y. If I and j are 0, then return 0. Otherwise, if xi and yj are the same, then call yourself recursively LCS of x, y, I minus 1, j minus 1 plus 1, etc. It's exactly the same code or the same algorithm that we used, but its running time is very different. There is no issue with the correctness of this code. It's correct. What's the running time? Think about the case that xi and yj are always different. X are always a's, y are always b's. Why does this case takes more time? Because now we have two calls to the recursion. Right? Instead of if xi and yj are the same, then there is one call of the recursion. Here I have 2 calls of the recursion. What would be the running time here? Quite bad. because I start when I think about the case of 3, 4. And in the case 3, 4, x has 3 characters, y has 4 characters. In the case of 3, 4, one of the sub-cases of the ij, remember, xi and yj contains very different characters. What can go wrong? I need to solve the case 2, 3. In the case 2, 3, the first 2 characters of x, 3 characters of y, I called it once here, and I called it once here. And if my algorithm is not memorizing that the solution didn't change, it's the same substring, then the running time suddenly becomes exponentially. The running time will be 2 to the m plus n in the worst case. Why? Because you didn't realize that it's the same solution, it's the same length of the solution, it's the same subproblem. Now the whole of the list of properties of dynamic programming that I had these cryptic slides earlier starts to make sense. I'll use dynamic programming because the LCS problem I can solve by identifying all the subproblems that I need to handle. I don't know what is the optimal matching, so I need to check all the pairs of ij as the last characters. But how many subproblems do I have? The moment that I tell you what is I and j and compute what is C of I and j, the answer is unique. It will be always the same for the same strings x and y. So I can solve this subproblem once, and I don't need to worry about it again. Again, our nice analogy S. The moment that I figure out what is, I want to know the distance to t, but the moment that I figure out what is the shortest path to v, then this shortest path doesn't care any bit how are you continuing on your way to t. The shortest path to v is unique no matter how you continue. That's why in the shortest path, the number of subproblems is only linear, 1 per each vertex. OK. Here is one of the cutest examples of dynamic programming, not LCS. And something that I made this morning. So the motivation are problems in printed board or CPU's design where you want to connect nodes by a network. So a few definitions. I have points in the plane. And I want to create some network that connects all of them. Actually, I want to take even a smaller example. Here is my network. I have 3 points. I'll call them terminals. P1, P2, P3. That's my example, not from the book. P1, P2, P3 are my terminals. That's their location. And I want to connect them by a network so that everybody can talk or connect to every other point out of these 3. So let's try. I'm trying to minimize the total length of this network. So I can use all the 3 edges. It's connected. P1 can talk to every other one. But if I use all the 3 edges, our length is 1, I'll spend altogether 3. And since I just cared about connectivity, not about the path being necessarily short, I can do it with only 2 of them. And then the length is 2. The length is 1 plus 1, which I think we can prove it. That's a result. Can I do any better? Not if I insist on the minimum spanning tree, that is, only use edges that are connected points, only edges that are between pairs of vertices. Can I find a better way to connect these 3? Better shape? Of these 3 points that I had on the right side. Once again, my only problem is walk or draw or pave roads or place fiber links between these three nodes. So each one can connect to everybody else. And the total length of these roads is as small as possible. This is a minimum spanning tree. I cannot do better than this. Yeah.
I guess, so is that what you use this for, or like kind of trying to come up with how you're doing a network?
Yeah, but the solution to this problem, I mean, minimum spanning tree is easy to compute. Find the graph and look at, find the graph and look at all the edges, and then you are sorting, for example, the weights of all the edges and try to add each edge from the cheapest to the most expensive. But for every edge, you are checking, does it help me connectivity or not? If it doesn't help connectivity, then I ignore it. But it's not the minimum spanning tree problem that we are trying to solve here. I just want to connect all of them. Help? Yes. So one way to do it with cheaper weight would be connect them in the way you suggested. I'm not putting my next that it's cheaper. I think that it's actually more than 2. But you are completely in the right direction. It's one of these cute questions that you can solve by placing nails, putting them in water with soap. And you are pulling it up, and because soap bubbles tries to get minimum surface, you'll get your solution. Play YouTube with this. Sorry.
We can make 3 perpendicular lines on each of the P1, P2, and P2, P3, and P1, P3, and then take that point in the middle.
White. So I'll add this point in the middle. That I agree, and?
And then just draw a line to P1, P2, and P3.
Everybody agrees with Sammy? So take this point in the middle. It's called Steiner point. Steiner point. And the whole tree is a Steiner tree. And yeah, that's what you're finding. And you can easily check the length of these guys is less than 2. And by the way, finding Steiner tree in graphs, I'll give you a graph, and I want to ask you, make sure that all the vertices, that in this graph, I'll show you a set of vertices that I'll say, these are the terminals. These are important ones. Other vertices you can use if you want, but you don't have to. Well, as opposed to the minimum spanning tree, Steiner tree is in general NP-hard. In the geometric sense, you can approximate it quite well. Maybe we'll have time to discuss it. But we're in the dynamic programming. So in the dynamic programming part, I have a few constraints. Like generally, when you look at printed boards, edges will tend to be parallel to each other. So I assume that all the edges in the networks that I'm going to find. In my little drawing, I have an input of 7 terminals, P7, P6, P4, all the way. These are my terminals. And I'm trying to connect them by a network. And I want this network, or this tree, to be as short as possible. You can add vertices if you want, if it helps you. But you don't have to. However, the input terminals, P1, the P5s must be connected. And there is something that suggests dynamic programming here, that all my points lies on one of 2 lines. Okay, so it takes me much longer to explain what is a problem. Let's see what is a solution and why dynamic programming helps. So everybody understand? Find a tree connecting all the points. You can add Steiner point. D over here is a Steiner point. It's not one of the original vertices. I added a vertex over here. I want all the edges to be either vertically or horizontally, that is 90 degrees to each other, or parallel. And let's think about this algorithm. So here are my 2 lines, and let's say P1, P2, P3, and P4, and P5. That would be a good enough example. I want to try to do greedy. Greedy would mean connect every point to the previous point. Connect every point to the previous point and go, of course, left to right. I gave the points to you in order from left to right. We're in the part of the solution on the whiteboard. So I'll sort the points from left to right. All the terminals. Remember, Steiner is up to me to decide where. And even in geometric setting, finding Steiner tree without all these other constraints, finding Steiner tree is still NP hard. But here is the aha moment. So I'm trying to connect all these points. I'm proceeding left to right. Obviously, I'll start at P1. The 2 lines are just the 2 lines. These are not part of the network. I just wanted to show you where the terminals are, either on this line or on this line. And they are parallel to each other. So sort the points, progress from from the left to the right. So P1 to P2, presumably I'll use this segment, maybe. P3 to P4, I'll use particularly this segment, especially if P3 comes after P4, maybe. But now I need to go to, P3, and then I'll go to P4, and let's think about it. How do I reach from this part to P4? Well, I can go down over here and go to the left, one option. Or I can move a bit to the right and then go down. That would be an alternative option. Or I can go all the way up to P4 and then goes down. OK. Now, let's assume that if I need to go like this, go down and to the right, I'll always try to stay in the same place that I am all the time, as long until I got the x-axis. Right? All these solutions that I just showed you have exactly the same length. So I'll assume that it's a green one that I'm using, if the one that I'm using. So far, I didn't show you any dilemma in my life. Where do I have dilemmas? Let's think about adding P6 over here. And the distances are not necessarily the way that I showed you. That's topologically the part that is P3, P4 would be on the other side and to the right of P4, P5, and P6. Do you see any dilemma right here? How do I get to P6? Sorry?
Again, you have to move up from the P5 to P6.
That's one option. So one would be from here, go up and do the L. Or use this segment. Or use this segment that will continue. That is, don't go from P5, but continue over here, which maybe is what you need to do if P5 and P6 are much more to the right. So when I'm adding PI, I have the option of either coming up straight from the previous point, or do your L from the previous point on the other side. These are the only 2 options that you have to say. That is, from a solution of the set P1, Pi minus 1. Let's say that we have a solution of P1 to Pi minus 1 to obtain a solution of P1 to Pi, we only need to know there are only two options. It's dynamic programming, but it's dynamic programming where when I'm adding 1 point, I'm from the solution to the Pi minus 1. I'm adding Pi. I want to know if to Pi, do I go is straight? Sorry, the S is missing, ADHD. If the, no, seriously, is straight or L shape. By the way, English is my second language, but it's not that in Hebrew I don't have spelling mistakes. OK, that's the only decision that I need to know. So what do I need to store at every moment as the algorithm progressed? I need to know, here is my 2 lines. Here is Pi minus 1, and here is Pi. I need to know what is the optimum solution where Pi was obtained in this way. I need to know what is the optimal solution where Pi was in L shape, that is, go from somebody previous, go up via an L shape. And that are stored in C L shape of I minus 1. It's a table, but it's a table with 1 cell. And there is one more table, C of straight, that assumes that into Pi minus 1, I arrived by a straight segment. And then to go from Pi minus 1 to Pi, I need to go down or connect to the previous one. So essentially, you just keep 2 values, and that's all the decision that you need to do. How did I get to the last point, or what the last point looks like? And from the 2 solution for Ci minus 1, you can get the 2 solution for Ci. You are computing the 2 values if you need to go down or you need to go straight, and of course, it's simple solution. I'll ask more details in the homework. Let's move to edit distance. I just wanted to at least introduce this problem, not fully explain it, but introduce this problem because it's a case where dynamic programming really saves you. You are keeping 2 options instead of 1 option. It's not greedy. But the table size, the difference of subproblems, is only 2 at each moment rather than n square that we had in the LCS. Let's talk about edit distance. Edit distance is a very close relative to the LCS. And they are both very much related to the difference between files. Like, where are these algorithms so important? You're doing incremental backup. What is incremental backup? On Sunday, you stored a copy of all your files on the cloud. That's what you did on Sunday. And then Monday, you're just storing what has changed from Sunday till Monday, and you store this part. And from Tuesday, you're just asking what has changed from the previous day till today. So we just want to know what are the diff files. But what is the shortest representation of the diff files? It's either expressed in the LCS or in the edit distance. More in the edit distance, if you do diff between 2 files, in Unix or most editors have this option, you'll see exactly the matching between the rows, which brings us back to the LCS. Edit distance in the last minute that I have, just a quick explanation, quick introduction. Edit distance between X and Y is defined as the minimum number of operations that you need to invest to that when you start on X and in the end of the sequence of operation, you'll get Y. That is, how can I get from the string AABA to the string AABA with minimum number of operations? 0, in this case, that's the simplest one. It's the same string. How can I get from AAA and get into AABA? You have a few options. You can take this A, make one replacement, make it a B, and do one insertion. Or you can do insertion of the B right here. Then it's just one operation. You can do delete everything here and then insert everything from scratch, but that's even more operation. I want the minimum number of changes. Right? Going from here to here, you have to perform for deletion and so on. Where is this so useful? Because you want to ask, if I just typed the word hello and you try to correct my spelling, and you look at your at the English dictionary, and the word hello appeared somewhere, the word day appeared somewhere, and the word nice appeared somewhere, and you ask, what is the probability, or how many typos do I need to generate if what I meant to write is this, and instead that's what I type in. How many errors do I have from here to here, which is just inserting this W by mistake, and so on. So I may want to ask what is the closest string edit distance-wise or error-wise, and what's the probability that it happens. And Occam razor, you know, I'll try to find what is the simplest explanation, the most likely explanation that gives me this, if that's what I had in mind. And that's exactly edit distance. Thanks, everybody. Questions? I'll add more details about the Steiner tree. I'll add more details in the slides. Questions? Zooms? Okay. This is on the. This is should be updated. You have it? No? Oh, maybe I didn't add the link. Sorry. Look at the normal link with the ending D. Can you check it? dp2.pdf. dp2.pdf. If you just the same ending like everything else, dp2.pdf.